In this module, you'll learn how to compare NVIDIA GPUs, Google TPUs, and Huawei Ascend NPUs in a structured way. We'll turn raw specs and marketing claims into a practical selection framework you can apply to your own projects. AI data centers are no longer built around a single type of accelerator. As models grow from millions to billions of parameters, you quickly hit limits in cost, energy, and throughput if you only rely on general-purpose GPUs. Instead, three hardware directions now coexist. Large H100 and H200 clusters still dominate flexible general workloads. Cloud providers use TPU pods for highly optimized, large-scale training, and many regional or enterprise deployments adopt Ascend-based data centers for tightly integrated, cost-sensitive AI. Modern ML engineers need to understand how to exploit this mixed hardware world. Each of these accelerators reflects a different design philosophy. NVIDIA H100 and H200 remain general-purpose GPUs. They give you maximum flexibility. You can run deep learning, graphics, scientific computing, and custom CUDA kernels on the same device. Huawei Ascend 910C and 950 move closer to an AI-only mindset. Their Vinci cores and matrix engines are tuned for data center AI pipelines with high on-chip data flow. Google TPUs sit at the extreme, domain-specific chips whose systolic arrays are optimized almost purely for massive dense matrix multiplication. At a high level, all three accelerators follow a similar recipe. Lots of parallel compute units, plus very fast on-package memory, tightly wired together. NVIDIA GPUs mix general-purpose CUDA cores with Tensor cores. CUDA cores handle flexible control flow, while Tensor cores crush matrix multiplications in low precision, fed by large HBM stacks. TPUs focus almost entirely on one thing: a giant systolic array for dense matmals, streaming data through from nearby HBM. Ascend's Vinci cores blend vector, scalar, and dedicated tensor units, tuned for AI operators, again sitting next to high bandwidth memory to keep those units busy. Once you move beyond a single accelerator, the way devices are wired together becomes as important as their raw flops. NVIDIA leans on NVLink and NVSwitch to create very high bandwidth, low latency connections between GPUs, ideal for tightly coupled workloads like large model training. Google's TPU pods use a toroidal mesh, so each chip talks to its neighbors in a grid. This scales well for synchronous data parallel training. Huawei's Ascend systems combine PCIe with their own fabric, balancing compatibility with specialized links. In practice, your scaling efficiency is largely determined by this interconnect topology. Even if the raw hardware is extremely fast, your real-world performance depends heavily on the compiler and runtime layer. Your framework, PyTorch, TensorFlow, JX, or Mindspore, describes the math, but CUDA with KDUNN, XLA on TPUs, and Huawei's CAN decide how that math is scheduled and optimized. This layer handles global graph optimizations, fuses operators into larger kernels, and chooses where tensors live in memory. If these compilers are immature or misconfigured, you'll leave a huge amount of H100, TPU, or Ascend performance unused. Ecosystem maturity also shapes how fast you can ship models. With NVIDIA, you get very deep low-level tooling like Nightsight and CupTI, plus massive community support. If you hit a problem, someone has probably seen it before. Google's stack is excellent if you live in the TensorFlow or JAX world. Tools are more graph-centric, and community help is strong, but mostly inside those ecosystems. Huawei's tools are tightly integrated and improving quickly, but global community resources and open-source examples are still more limited. Different accelerators like different workloads. For Vision and classic CNNs, all three platforms do well. H100 and H200 give strong, general performance, TPUs, handle big image batches easily, and Ascend's cube units are highly tuned for convolutions. For transformers and large language models, H100 and H200 shine because of massive HBM and bandwidth. TPUs can scale very far using XLA sharding across pods. Ascend can also work, but you'll spend more effort tuning communication. For sparse and recommendation models, NVIDIA's mature embedding support is strongest. TPUs and Ascend are more sensitive to sparsity patterns and layout. Deep optimization for a single vendor quietly increases lock-in. Custom CUDA kernels or deep speed tricks make it painful to leave NVIDIA. XLI-specific assumptions and JAX PMAP patterns tie you to TPUs. Can-only operators or Mindspore features anchor you to Ascend. Your model weights might be portable, but the training code and performance tuning usually are not. To move more freely, you need common abstractions like OnNex or high-level framework APIs, and that almost always means giving up some low-level, hardware-specific efficiency. Choosing hardware also means choosing a deployment model and a vendor relationship. NVIDIA is the most flexible. You can rent GPUs from almost any major cloud or buy servers and run them in your own data center. That's great for hybrid setups, but demand and pricing can be tough. Google TPUs are different. They're powerful and cost-efficient, but only inside Google Cloud, so you trade flexibility for simplicity. Huawei Ascend has strong regional traction with tightly bundled solutions, yet availability and export controls can significantly shape where and how you deploy. A practical way to decide among these accelerators is to start with your primary constraint, not with specs. If you need maximum flexibility, want to stay cloud agnostic, or rely heavily on PyTorch and rich ecosystem tools, NVIDIA H100 or H200 is usually the safest bet. If your priority is training huge dense models and you're already committed to Google Cloud with TensorFlow or JAX, TPUs give you excellent throughput and tight integration. If you operate in regions where Huawei is dominant, need on-prem appliances, or must integrate tightly with telco or enterprise gear, Ascend 910C or 950 can make more strategic sense. Here's how to apply this trade-off matrix in practice. If you want maximum versatility and the broadest ecosystem, H100 and H200 are the safe, industry-standard bet, especially for large language models and mixed workloads. If your workload is mostly dense, well-structured models and you're already committed to Google Cloud, TPUs can deliver excellent performance, but you accept tighter lock-in. Ascend shines where it's readily available and regulated for use, especially for CNN and matrix workloads, but comes with a more regional, Huawei-centric ecosystem.